Okay, so last time we started chapter two and kind of continued chapter two into lab last time as well. And we were talking really in chapter two, the first part about waves and sort of properties of waves. So remember, we have our wavelength, which is basically the length there from peak to peak. Or trough to trough. We also have our frequency, which is sort of how many waves pass a particular point per second. It typically has units of reciprocal seconds. 1/seconds are a hertz, Hz, and a reciprocal second is basically the same thing. So there's a one-to-one relationship between those two things. And again, usually our wavelength, a lot of times are in meters. Sometimes it's given in nanometers. But usually in sort of calculations, if you're going to do some calculations, you do need to sort of have it in meters, so everything cancels out correctly. We also saw that there's sort of a relationship that the speed of light, which is c, is equal to the wavelength times the frequency. So where are we at here? There we go. So we have sort of this relationship here that we saw, wavelength times the frequency. Again, lambda times the frequency, which is new. And again, typically this is in meters. This guy is in reciprocal seconds. And that's why when we do the speed of light, which is a constant, the 3 times 10 to the 8 number, it is per meters per second. We also talked about energy kind of associated with waves. So as waves are moving, they move and carry along with them, obviously, a certain amount of energy associated with them. Energy is related to wavelength. So the longer the wavelength, the lower the energy. And the shorter the wavelength, the higher the energy. And again, that's because the shorter the wavelength, the higher the frequency. So you can kind of think about it like it's moving really fast and it has a lot more energy rather than something with a longer wavelength can kind of be drawn out and not have as high of a frequency. It'll have a lower frequency and then would have lower in terms of energy. Now, when we talked about energy, there was an equation that we saw that related the two, which is E is equal to H times the frequency. Here, H is Planck's constant, which is that 6.63 times 10 to the minus 34 joules times seconds. And again, that's a constant as well, just like the speed of light. So you could use your frequency here to calculate the energy. We could also substitute both of those guys together like we talked about. Hc divided by the wavelength. The two top guys, again, being constants, which allows you, if you just know the wavelength there, you can figure out the energy associated with it. Again, the wavelength here would need to be in meters to make sure all the units cancel out correctly. We then sort of related this idea of sort of waves and light and the idea really of electrons as they basically transfer from one energy level to the next. They either need to sort of gain energy or lose energy to do that. And again, if the electron sort of is elevated to a higher energy level, it's going to gain energy. And if it is going to eventually want to work its way back down, it's going to give off that energy in the form of light here with a wave with a specific wavelength associated with it. So one is endothermic, one is exothermic when we talk about energy. And just a reminder that if you get sort of a positive number for energy, that means that it's endothermic. And that means that heat and energy is being absorbed. Opposite of that, typically if you get a negative number for something with energy, that means that heat and energy is being released, which is exothermic. So we had these equations here, and we specifically saw one that basically related sort of what happens as these electrons go from one energy level to the next. Remember that, excuse me, that when we talk about the energy levels, those are sometimes represented by n numbers, which is the principal quantum number. N equals 1 is the lowest in energy level. n equals 2 would be a higher energy, n equals 3, and so forth. So we could use sort of the equation that we saw the other day, that the change in energy is equal to minus 2.18 times 10 to the minus 18 joules. This again is sometimes referred to as Rydberg's constant. 1 over n squared final minus 1 over n squared initial. These again are the energy levels that the electron is transferring, and we could do this basically to figure out how much energy is required to do that. One thing that we did talk about is the idea that these things are quantized energy, which basically means, as we talked about, that if an electron was going to go from, say, the first energy level to the second, it would gain enough energy to do that complete transition. Again, it won't find itself sort of in between energy levels or anything like that. Just like if it was coming back the other way and dropping back down, it would gain enough or lose enough energy basically to do that transition. And that's sort of the idea of quantized energy, as we talked about. Is kind of like, I think I used the staircase sort of analogy. Again, when we sort of walk upstairs, we're either, on this step, that step, we typically have enough energy going up or down to get from one step to the next. We typically just don't decide we'll lay it up halfway between two steps or anything like that. So that's more of a quantized energy. That's what sort of gives us those line spectrums that we see, and we talked about as well, for example, for hydrogen. Now, the nice thing about this as well is that is energy, which means we can also relate that to the other equations that we saw. So let's go this way. So we're running out a little bit of room here, so we'll go that way. So that E is also equal to H times the frequency, and also equal to HC over the wavelength. So even if you just know about the wave or the electron, for example, the energy levels it is transferring, you can relate the energy back to figure out the frequency of that wave, and you ultimately can relate it back to figure out the wavelength associated with that. Now, we did a number of those examples at the end of the lecture there in lab, where we calculated all those things. We calculated the energy, we calculated the frequency for each of those sort of waves that would be coming off, and we also calculated the wavelength. And I think there was a couple of questions last time about, sort of what are the units that you should do in terms of lambda, which is this guy here, which is the wavelength. That's lambda. And again, a lot of times it's in meters, but when we specifically talk about sort of the visible part of the spectrum, where we do see colors that red, orange, yellow, green, blue, violet, we typically do report those numbers in nanometers. So that's why the example that we did in lab, we reported the wavelength in nanometers, and that's because it just makes it kind of a more whole number. So it's kind of typically given in nanometers, but if it's not specified, technically you could give it in any unit you want for wavelength. That's sort of a length type measurement. Meters is very common. Nanometers is very common as well. Any questions on that stuff we talked about last time there? Okay, so again, remember, if you do have questions, feel free to ask however you want to do it, with your microphone, or you can, again, chat me a question as well. All right, so I think this is where we actually left off, sort of talking. And again, we also talked about last time there in lab, we talked about the idea of sort of an early theory of sort of what's happening with these electrons in terms of as they transfer from one energy level to the next. And that was sort of the Bohr model of the atom. And as we talked about, the Bohr model of the atom works really well to describe sort of the lines that we see in hydrogen, the sort of four colors that we see. But as we move away and we get to atoms that have more than one electron present, it really doesn't necessarily hold up all that well. So we are sort of in the process where we are sort of moving from the idea of these orbits to this idea of basically orbitals, where we really don't know how electrons are moving. I'm not sure. Is other people having any type of echo? see. All right, we'll try to fix it, hopefully, maybe. See if it's any better. Okay. So, we'll continue. Hopefully it won't be so bad, I hope. All right. So what we're doing is, again, sort of moving away from that model, which is sometimes referred to as the planetary model of of an electron or an atom, where it basically sort of circles in a circular path in these orbits around the nucleus. And as we'll talk about, and we have talked about a little bit, is that it doesn't really work that way. Electrons really don't travel in nice, pretty circles. They do pretty much travel very kind of randomly about. And one of the next sort of important sort of theories and ideas that came about was the one that was done by deBroglie. And we also talked about with Einstein the idea that perhaps there is sort of a dual nature of light, that particles can have wave-like properties and waves could have sort of particle-like properties under certain sort of situations. And that's what deBroglie really proposed. He proposed that particles could really have this wave-like behavior. He predicted that the wavelength of a particle is inversely proportional to its momentum. And because particles, for example, are so small, the wave character is very significant. So this is what is sometimes referred to as the deBroglie wavelength. So it's sometimes referred to as the deBroglie wavelength. And it is missing actually right here. It should have an S, seconds. So there's a seconds missed. So you might want to put it onto your notes as well. And it is H, which is our Planck's constant. So this is, again, our Planck's constant, which is our 6.63 times 10 to the minus 34 joules times seconds. It is times, and that is times our seconds. The mass here does need to be in kilograms, and the velocity here is in meters per second. So velocity, meters per second, mass in kilograms, and H, which is our Planck's constant. So why is that? We need to sort of have things in certain units. If we look at this, the wavelength equals H over our mass and our meters per second. So if we just kind of put the units in, one relationship that we also saw earlier was that a joule is equal to a kilogram meter squared second squared. So we saw that at the end of chapter 1, this relationship here. And if we put that in for our H up on top, we would have kilograms meters squared second squared times the second. And on the bottom, that is why we need the mass, not in grams like we commonly might think, but we do need it in kilograms so that they cancel. And again, our velocities in meters per second. So what ends up happening here, if we sort of look at sort of all the units and what is canceling out, because we have our mass in kilograms, they cancel. 1 second here cancels 1 here. The second one cancels the second one. And 1 meter cancels 1 meter, which means when it's all said and done, we will be left with the units of meters in this particular case. So the good news is it's still the same number here for our H, and you don't really have to do anything. You can even leave it at joules as long as you remember this part of it, that you do need to make sure you get that guy into kilograms so everything cancels out correctly. So you don't want to use it in grams. Again, you got to make sure you get that self to kilograms. Interesting about sort of deBroglie was he actually didn't do any type of experiments or anything like that. He just sort of came up with the theory, which was sort of later proven to be sort of correct as well, which was interesting. So that's an important, obviously, formula for you to know, which is this guy down here. This, again, deBroglie wavelength that can be used for, particles and that might not normally be thought of as having characteristics of waves. but we can sort of apply wave-like function to it. So why don't you give this a go and see what you come up with. When you've got sort of an answer, type it into the chat box there so we can kind of see where everybody is at. So calculate the wavelength of an electron that is traveling at 2.65 times 10 to the 6 meters per second. And I'll get you that mass there of a electron. So take a second and see what you come up with. Make sure that you do get it to kilograms if it's not given to you. That means essentially we're kind of good to go into our formula, which is our h over our m times our velocity here. And again, Planck's constant, which is our 6.63 times 10 to the minus 34. And this is essentially kilograms meters squared, second squared times seconds. And a reminder that really this part of it here is what represents the joules times seconds that we normally associate with it. That's going to be divided again by our mass here, which was already in kilograms. And also the other thing you want to make sure is your velocity is obviously in meters per second. Again, without that, it will not cancel out correctly when you use this. So again, you may have something like miles per hour, or, kilometers per minute or something like that. So you might have to at some point maybe do a conversion to get those guys into those units. But in this case, we're good to go because they are already there. So we got that. And obviously, as we talked about before, you definitely want to make sure that you are using your exponent button when you punch these guys in. So we would take our 6.63 exponent button minus 34 divided by 9.11 exponent minus 31 and divided by 2.65 exponent button 6. And it looks like we end up with we'll call it 75 times 10 to the minus 10, it looks like. Again, in terms of units, kilograms cancel, meters cancel one of them, seconds cancel, and we have our other seconds there will cancel as well. So get rid of that there. And we are left with meters that are left over there in terms of the units. Any questions on that particular calculation there? Okay. So again, that's the deBroglie wavelength. We use it to sort of calculate the wavelength of particles. Again, with this idea that we're talking about that, particles can have wave-like function, and waves also can sort of behave like particles as well. Any questions on any of that there? All right. So as we were talking about, and as we talked about with the Bohr model, that works well for that hydrogen, but really doesn't hold up once we get a lot more electrons sort of into the mix. So we really are going to be moving away from, as we talked about, the idea of sort of these electrons hanging out in sort of these orbits and basically flying around in these pretty little circles. So one important idea that sort of led us to sort of that understanding was the idea of what is sometimes referred to as the Heisenberg uncertainty principle, which went there. There it is. So the Heisenberg uncertainty principle, as I very much try not to cross it out, trying to underline it there. So the Heisenberg uncertainty principle is the idea that, we will never know sort of both the position or the momentum of a particle at any given time. And actually, as we know more about one thing, so for example, as we know more about the position, we start to know less about sort of how it's traveling and vice versa. And a particle such as an electron we really wouldn't know, like Bohr sort of described that, hey, they're moving in these nice, pretty circles. Again, if we just sort of hang out here, eventually that electron is going to basically come back around. And this is really the formula there for Heisenberg's uncertainty principle. This is position of a particle. This is sort of how it's moving, its momentum. And again, you can see it's greater than or equal to. And again, that basically means that, we don't really know exactly where it is. H is our Planck's constant. Pi is pi 3.14, and the 4. We probably won't do any of calculation, involving this formula. We pretty much won't. But it does help us move away from Bohr's model again to this idea that, again, the best we could kind of do is think about the probability of finding an electron, as it should be moving very much in a sort of unorganized, I don't say unorganized pattern, but a very random sort of pattern. So as we move away from Bohr's model of the atom, we move towards this idea of, we're not going to think about electrons hanging out in these kind of circular orbits, but they are going to hang out in these things that are really what are referred to as atomic orbitals. And what are atomic orbitals? Well, really, they're kind of probability maps. They're really theoretical probability maps of where there's a very high probability, perhaps, of finding an electron in an atom, or where there's maybe not a high probability of finding an electron in an atom. Just because there's an area, for example, of high probability of finding an electron, it doesn't mean you know how it got there, when it's going to be there, how it's traveling. All you know that, there's a pretty good chance in this particular area of the atom, we can basically find an electron. Now, these atomic orbitals you may be familiar with from Chem 100. That is your s orbitals, your p orbitals, your d orbitals, and your f orbitals. And these are things that we talked about with electron configuration, I'm assuming. And a couple of things about these orbitals, and we'll talk more about them as we go through here. We're actually going to figure out why there is, one s orbital, maybe why there's 3 different types of p orbitals and so forth. But a couple of things, any individual orbital as you may know, could hold a maximum of 2 electrons. So any individual atomic orbital that you have, the maximum number of electrons you could put in there. A couple other things that you might be familiar with in terms of the atomic orbitals, and we'll kind of see it as we kind of go through this chapter. There are s orbitals. And in terms of s orbitals, there's really only one type of s orbital, no matter what energy level you're on, which means if you maxed out the electrons for that guy, it could only hold really 2 electrons. Now, when we get to p orbitals, there's actually more than one p orbital. There's basically 3 different types of p orbitals. Now, since there are 3 different types of p orbitals, each one could hold 2 electrons. That means if you max out all 3 of those orbitals, you basically should have a grand total of 6 electrons. There are d orbitals. And d orbitals, there are 5 types of d orbitals. And again, if each one could hold a maximum of 2 electrons, that means that you got a maximum of 10 electrons you could put in there. And the last type of orbital we typically come across are f orbitals. And there are 7 different types of f orbitals. Again, each one able to hold 2 electrons, which again means if you were to fill up all of those orbitals, you would basically max out at 14 electrons. And again, some of this should be familiar with you if you remember sort of electron configuration. This is sort of what we're talking about here. Any questions on that so far? So again, this is moving to a more what is sometimes referred to as a quantum mechanical model. of the atom. Where again, it's really all about sort of probability of finding electrons in particular locations. So, sort of a question is why maybe we would want to know where our electrons are in the atom. It's important to know sort of where the electrons are for a couple sort of reasons. A is sort of electron configuration, so we know how sort of electrons go into the atom and where they're located. Also, as we'll be talking obviously in future chapters as well, depending on the location of those electrons and which electrons you may be talking about, there are certain electrons involved in bonding. There are certain ones that are too close to the nucleus to be involved in bonding. So there's like valence electrons, core electrons. So it's important to have sort of a general idea of knowing where the electron is in terms of energy level, because there are certain electrons, again, like I said, that are involved in bonding, which are obviously very important sort of functions and stuff like that. Here is sort of a probability sort of map here, and you can probably pick it up on the screen, but if you look kind of to the center here, it's a little bit darker. And then as we sort of fade out towards the edges, it gets lighter and lighter in color. And usually when we look at sort of a probability map, that's usually a very high probability map where it's very dark in color. And as it gets lighter in color, there's a less of a probability of finding an electron. And that's what we can see here on this kind of graph. The distance from the nucleus, we see that there's probably a pretty high probability of finding an electron here near the nucleus, right? So as we sort of move away from the nucleus, there's less of a chance. So some of that is what we talked about before. Obviously, as we talked about before, the nucleus is essentially positively charged. Electrons are essentially negatively charged. So definitely those electrons in the lower energy level near the nucleus is going to feel an attraction to the nucleus. And obviously that's why there's a pretty good probability of near the nucleus you should find some electrons. But depending on the element in the atom, as you get kind of further away from the nucleus, there's a less and less probability of maybe finding an electron out there. Again, for some reasons, like it maybe has lost some electrons along the way as well, because they're not going to be held as tightly. So again, you just sort of visualize this idea here. And the center is sort of the nucleus. And again, high probability in near the nucleus area. Again, not really sure exactly how the electron is or moving, but again, you can see it gets a lot less probable as we move further away from the nucleus. There's something, as we'll talk about as well, the idea was sometimes referred to as shielding. So these lower electrons shield that positive charge from electrons further away, so they're not held as tightly as well. Also why, certain electrons are involved in bonding, while others are definitely not involved in bonding because they're too tightly held. So when we talk about orbital size, it's difficult to define sort of precisely. Orbitals is basically wave functions. So there's something known as Schrodinger's equations. If you ever end up taking physical chemistry, you'll see a lot about that. And it's a lot of crazy calculus type equations. But essentially what it is, again, is this idea of sort of probability maps for these different orbitals and sort of the shapes that they have. And for example, if we look at hydrogen, and just to kind of tie it a little bit to electron configuration as well, hydrogen has basically one electron. And basically on that first energy level, that is what we have there, is basically a 1s orbital. And we would have that one electron there. So we would have something like 1s1 in terms of the electron configuration. A couple of things what these numbers represent in case you maybe don't remember. So if you write electron configurations such as this, which we'll do some more of a little bit later on in this chapter, but this very first number is really the energy level, and that is what is referred to as the principal quantum number, which is a fancy word for basically the energy level. Obviously, the S represents the orbital that the electron is in, and the one up on top represents how many electrons are in that orbital. So when we have that, we have this one electron, it goes in, and as you can see, it actually would only have room for one more electron before that orbital would be filled. So there definitely is sort of an order as to which electrons go in. But let's talk first off, though, about quantum numbers. And quantum numbers really are sort of how we get to the orbitals that we have, how we get to how many orbitals we have on what energy level. It's really, sort of how we determine those things. So let's talk about the different quantum numbers first. So a couple of things here. Let's do that. First off, as I just mentioned, the principal quantum number is abbreviated as an N. And N that equals 1 is the ground state. And that is the lowest in energy. Is obviously closest to the nucleus, as we might have mentioned before. Anything N equals 2 to 7 is what are referred to as excited states. And these are definitely higher in energy. Now, the next one is the angular momentum quantum number. That has an abbreviation of L. Now, L basically tells you the shape of the atomic orbital. So when we talk about the shape of the atomic orbital, we're talking about, is it an S orbital? Is it P orbitals? Is it D orbitals? Is it F orbitals? So that's what L basically will tell us. L could have values of 0 to n minus 1. So it could have values of 0 to n minus 1 are all what are sometimes referred to as acceptable values of that quantum number there. Now, the next quantum number is the m sub L. The m sub L basically kind of tells us the orientation of those orbitals in three-dimensional space. And m sub L can go from minus L to 0 to positive L, all whole numbers there as you go across. And it really does sort of tell us, what is there in terms of how many of these orbitals are present. There is the fourth quantum number, which I think is on the next slide, but I'll put it here. It is the spin quantum number. The spin quantum number, ms, can have a value of plus or minus 1/2. And what the spin quantum number really kind of talks about is the idea of, when you do put those orbitals in, the electrons in these orbitals, it basically could only hold 2 electrons. By I'm going to say that right. By sort of the rule here, when the first electron goes into the orbital, it always goes in pointing in the upwards fashion. If this arrow represents an electron, pointing upwards is what is referred to as having plus 1/2 in terms of its spin. And the second electron will go in the opposite location, which is pointing downward, refers to basically having minus 1/2 spin. The electrons have their own sort of magnetic field as well. And as they're spinning, they are usually go into the orbital always opposites of each other. This is what is sometimes referred to as having paired spin in terms of those electrons. Basically, they're going in opposite directions. And the reason for that really is what is sometimes referred to as Pauli's exclusion rule, which basically means that no 2 electrons can have the same 4 quantum numbers. So Pauli's exclusion rule, which I think might be coming up somewhere. Where's that thing? No. Where'd he go? All right, we'll come back here. I was right here. So Pauli's exclusion rule basically says that no two electrons in the same orbital can have the same 4 quantum numbers. So it really is the spin quantum number that helps us get around that they don't have the same 4 quantum numbers. That's what that badly written there is quantum. And again, because one would have minus a half for a spin and one would have plus a half for a spin. And again, we'll get into that here in just a second. And it'll probably make hopefully more sense in terms of what's going on. But before we do, let's kind of skip ahead and just since we started talking about these orbitals, just to make sure here real quick. Let's just talk about those orbitals real quick and what they look like. So we'll skip ahead a little bit here. Okay. So just to make sure everybody is on the same page in terms of sort of what each of these atomic orbitals look like, let's talk about them officially here. So the first atomic orbital is the s orbital, and the s orbital is basically a sphere, and we do see the s orbital basically start to appear at the n equals 1 level. So these are basically s orbitals. 1s means is on the first energy level, 2s is on the second, 3s is on the third energy level. So s orbitals, again, a reminder, there are only one type, which means, again, it can max out at 2 electrons. It starts at the n equals 1 level. The next type of orbitals are p orbitals, and there are 3 different types of p orbitals. P orbitals, as we'll see, actually starts at the second energy level, and there are the px, the py, and the pz orbital. They are basically on different axes here on like a math Cartesian plane here. So we got the x, we got the y, and we got the z. They basically are kind of like a figure 8 type of shape. So p orbitals have this sort of figure 8. There's a part here where the node is. This is sometimes referred to as the node, which means a wave. When you have a wave as it's traveling, there are certain points where there's no amplitude, right? And that's basically what we're talking about here. So you can almost visualize that the nucleus is sort of here, which is why we would expect to find a lot of electron density sort of in this area when we talk about these sort of orbitals. And we have the px, the py, and the pz. Because there's actually 3 different orbitals here, these are sometimes referred to as the 2p subshell, for example. So a subshell represents all 3 of these individual orbitals. So the subshell represents all 3 of these individual orbitals, which means if you filled up the 2p subshell in this particular example, you would max out at 6 electrons. Any questions on that there? Now, we then have our d orbitals. And our d orbitals, there are 5 different d orbitals. They kind of look like 2 p orbitals together. We have xz and so forth on their different sort of locations. We have one where it looks like a p orbital with a donut in the middle. But again, these are the density maps that we were talking about, the probability maps. And again, you can see a lot of the highest probability are near sort of that node where it would be. And again, that's how we sort of get the shape that we see below by sort of outlining these probability areas where we'd have high probabilities of finding electrons. And again, as you can see coming through here. all 5 of these guys represents the d subshell. All 5 of those individual orbitals represents the d subshell. And again, since there's 5 of them, that means you would max out at 10 electrons, as each one could hold basically 2. Any questions on that there? And lastly, we usually stop here at f orbitals. There are 7 different f orbitals, as you can see. Again, their locations. And again, if you take all 70 of these guys together, that is the 7 F subshell. And if you max it out, you would max out at 14 electrons. Any questions about those orbitals? And those are the ones where, again, if you remember sort of writing electron configuration and such, that is essentially, you know, the where we're putting these things. These again are sort of, as we saw a little bit in the last slide, more probability maps. So, you know, you probably wouldn't necessarily find, obviously, you know, these shapes in the atom, but again, they're just sort of areas where there's high probability of finding electrons basically in the atom. So let's go back now that we sort of officially talked about sort of these different atomic orbitals, and that's what each of these guys are. Let's go back and sort of see how this ties to really the quantum numbers that we've been talking about. So let's just start with really the very first energy level and how we could figure out sort of what is going on that very first energy level. So I'll do it over here. Let's say that n is equal to 1. So that is the first energy level. That is the ground state energy level. What would L equal? Well, L could go from 0 to n minus 1. So obviously n is 1 in this case. 1 minus 1 is 0, which means in this particular case, L would equal 0. What would M sub L basically equal? M sub L could go from minus L to 0 to plus L. So since L is 0, the only option you could have for M sub L is 0 as well. And M sub S, for each of these M sub L's, could be plus or minus 1/2. So what does that really sort of mean? Well, what it means is, let's actually talk about what each of these numbers sort of really represent. First off, n equals 1 means we are on the ground state. And that is basically, I'll draw it down here maybe. N equals 1 is the lowest in energy. It is closest to the nucleus. Now, if you remember, L, which is the angular quantum number, basically tells you the type of atomic orbital that's present. And when you have a value of L is equal to 0, that represents an s orbital. So what that is telling us, of L is equal to 0, there's no other numbers there. That means that this orbital that we find on the first energy level is an s orbital. And we would represent that as a 1s orbital. Again, the 1 means we're on the first energy level. And the only guy there is basically an s. How do we know how many there are? Well, M sub L is basically only one number. So this is basically, if you want to think about it, how many. So there's only one. So we would represent it by just one line. It's really the orientation, but in case you could also think about it as how many there are. And what does that M sub S mean? So the M sub S means that if we were to put some electrons into that orbital, again, it could only have 2 electrons. The first one would go in, And again, that means that the m sub s would equal plus 1/2 in that case, with the arrow pointing up. And the m sub s would equal minus 1/2 with the arrow that needs to go, based on Pauli's exclusion rule, in the opposite direction. First off, any questions on what each of those numbers represent? Okay, so why do we really need to sort of put it in opposite directions? So remember that Pauli's exclusion rule was no two electrons in the same orbital can have the same 4 quantum numbers. So let's just say, for example, you want to violate that rule and you say, I don't care. My n equals 1 is going to have both electrons heading in the same direction. So as we will see as we go through these, we will see that you can assign quantum numbers for every single electron individually. So if we take this first electron and we were to assign the 4 quantum numbers, the n would equal 1 because it's on the first energy level. Because it's an s orbital, L would equal 0. M sub L would equal 0 in this case, and M sub S would equal plus 1/2. Now, if we did it for electron 2 that is sitting there, in the exact same orientation, as you could probably imagine, it is going to come out exactly the same. N would equal 1 for that electron. L would equal 0. M sub L would also equal 0. And M sub S would equal plus 1/2. That is a violation of Pauli's exclusion rule. Both of these electrons have the exact same 4 quantum numbers, which you cannot have. So how do we get around that? We basically flip the second electron going in the other direction. So when we do the 4 quantum numbers for this guy, n is equal to 1, L is equal to 0, M sub L is equal to 0. And now the slightest difference is it is minus 1/2 for the spin, which gives that first electron, which has these quantum numbers, and the second electron, which has these quantum numbers. There is a difference. And the difference is this big difference of how the electrons go in. And you would end up the same way if you decided, well, what if I just send them both in upside down? They both would end up with these same 4 quantum numbers, which would also violate Pauli's exclusion rule. So that is really the backstory for why when we put electrons into individual orbitals, they need to have different quantum numbers or different spins, because if they have the same spin and they're in the same orbital, they will violate Pauli's exclusion rule. Any questions on that there? Okay, so now that we know what's on the first energy level, let's talk about maybe what's on the second energy level. So obviously at this point, if we look at the bottom here, we are full, right? We cannot put any more electrons in that orbital, which means we need to put electrons in the next orbitals. And where are the next orbitals? Well, the next orbitals would be on the n equals 2 level. So let's go through the 4 quantum numbers for n equals 2. So you could hopefully maybe see what's going on. So for n equals 2, again, L could go from 0 to n minus 1. So in this case, 2 minus 1 is 1. So L could have a value of 0 and I do the math right, 0 and 1 there. So this is different than what we see on the first energy level. If you remember, on the first energy level, we had just 0, but we actually now have a 1 there. So when we have an L value of 0, that represents an s orbital. When we have an L value of 1, that represents a p orbital. So that actually represents a p orbital in this case. So what is this really telling us? This is really telling us that when we go from our first energy level, which based on the quantum numbers, there is only an s orbital. When we get to the second energy level, there is also an s orbital, but that's where we start to see p orbitals basically first start to develop. Now, when we get to a situation where we have multiple L values, for each L value, you could do a M sub L. So the M sub L again is minus L to 0 to plus L. So in the case of L equals 0, M sub L would equal 0. So what that tells us is, just like we saw in the first energy level, there is only one type of s orbital present on the second energy level. And in that orbital, we could basically put an electron up and down. But now when we go to the L is equal to 1, we can also calculate the M sub L for that particular p orbital. And what it is going to be is, since L is equal to 1, it would go from minus L, which would be minus 1, to 0 to plus 1. These are the 3 values that you could have for those p orbitals. And how many p orbitals do we know we usually have? That is why we have 1, 2, and 3 p orbitals, representing the 2px orbital, the 2py orbital, and the 2pz orbital. And that's actually what those numbers represent. They go right in order: -1, 0, and +1. So that's what each of those represent. Now, in each of those individual orbitals, the px, the py, and the pz, each of those could have an electron with plus or minus 1/2 present. Question on that. So based on these quantum numbers, this is why we do not see our p orbitals appear until we get to the second energy level. But in addition, we also see our s orbital that's present. Any questions on that there?
I have a question.
Yeah.
So we don't have anything in our s orbitals because it's 0, right?
Right. So technically the M sub L for this guy would be 0. So what I wrote in here are the M sub L numbers, but it would be technically 0 for that guy. So technically this is the orientation of these orbitals in 3-dimensional space, but also what it tells you is like how many there are. So since 0 is just one number, there's only one orbital, and obviously -1, 0, and +1 are 3 total numbers, which represents 3 different p orbitals, basically oriented in 3-dimensional space differently on the x and y and z axis. Other questions on that? Okay. So then let me continue on here and kind of build up a little bit. Let's then look at what happens when we get to the n equals 3 level, which is the third energy level. So if we have the n equals 3, we then can have an L value. Again, is going to go from 0 to n minus 1. So n minus 1 is 2. So we would have a value of 0, 1, and 2 being present. So obviously we've already talked about that when you have an L value of 0, that represents an s orbital is present on that energy level. So we would expect obviously an s orbital to be there on the third energy level. Just like we just saw, when we have a value of 1 for L, represents a p orbital. So on that third energy level, we would expect to see p orbitals. And now we have an L value of 2, and an L value of 2 represents d orbitals. So this is why when we get to the third energy level, that is where we first start to see our d orbitals appear. So n equals 3. For each of these, just like we did above, we could do an M sub L, and it would be 0, just like it was previously for our s orbital. So that tells us that we have a 3s orbital that's present on the third energy level. Just like we did on the second energy level, the M sub L for this guy would be -1, 0, and +1. So just like we saw on the second energy level, we would also have 3px, 3py, and 3pz orbitals happening. But now we have our 2. So if we were to do our M sub L for 2, it would go -L, which would be -2, then -1, again going whole numbers, to 0, +1, and +2. And when we count how many numbers we really have here, we have 1, 2, 3, 4, 5 numbers. And that is why we have 1, 2, 3, 4, 5 d orbitals. I guess that will write this way. These are actually 3d orbitals. And again, the numbers really do just go exactly like we did there in terms of the M sub L, -2, -1, 0, +1, and +2 happening here in terms of the M sub L number. And this guy would have the -1, the 0, the +1, and then obviously this guy would be 0. And again, what I'm writing there is the M sub L numbers for each of those orbitals. And each of these individual d orbitals can have an electron that is plus or minus 1/2, either up or down. So this explains again why when we talk about sort of d orbitals do not appear until the third energy level, it's really because of these quantum numbers, tells us the probability maps and all that, that we won't start seeing those type of orbitals until we reach that third energy level. Any questions on that one there? I'm gonna go one more here just to make sure. So why don't we go to the next energy level? So why don't we do n is equal to 4? So on the fourth energy level, if n equals 4, again, L would run from 0 to n minus 1. So that is going to be 4 minus 1, which is 3, which means we would have values of 0, 1, 2, and 3. And just like we've seen before, an L value of 0 is S. So on the fourth energy level, we again see S orbitals present. An L value of 1 represents p orbitals. So just like the second and third energy level, we start to see p orbitals there as well. L equals 2, as we just saw, is our d orbitals. So just like in the third energy level, we have our d orbitals, but now we have an L value that is equal to 3, and that's our good friend f orbitals that are going to be represented by an L value of 3. So these guys are going to represent our F. And just like previously, our 0 would yield our M sub L of 0, which means we know we would have a 4s happening there. We would have our 1, which would yield an M sub L of -1, 0, and +1, which again would give us, I know I'm going to run out of room, so I'm going to write them smaller. That'll give us our 4p orbitals, the 3 of them. The d, as we just did previously, would give us an M sub L of -2, -1, 0, +1, and +2, which is our 5 d orbitals. And now with our F, we'll go this way. So our F is 3, which means for our M sub L, we would start at -3. Again, going whole numbers, -2, -1, 0, +1, +2, and +3. And I'm going to hope when we count those up, that is 7 of them, which is why when we talk about f orbitals, there are 1, 2, 3, 4, 5, 6, 7 f orbitals. And again, the numbers roll just like that in terms of the M sub L. and here. So it's not until we get to the fourth energy level that we actually, again, do start to see the presence of those f orbitals based on the quantum numbers. Question on that one there. Now, electrons do go in, obviously, at the lowest energy level. Once they get filled, they go to the next one, and they go to the next one until they, you know, obviously distribute all the electrons that you need. Now, a couple of things here. Some terminology, as I sort of touched upon earlier. You know, there is sort of a couple of words that we sometimes see when we talk about this. So let's talk about, actually, let me just kind of redraw this on the next page one more time. So again, our n equals 1, 1s orbital, n equals 2, 2s, we see our 2p, n equals 3, 3s, 3p, and our d, and our 4s, 4p, 4d, and again, our f's happening here. And one more. Okay. So there's a couple of words that we sometimes talk about. So first off, when we talk about this, is sometimes referred to as a shell or a level. So those are two words that are sometimes used. So when we talk about, you know, what is the maximum number of electrons on the, we'll go with the n equals 2 shell or level. Why don't you take a second and see what you think the answer is, and we'll talk about what it is. So just take a second and think about how many total electrons, if filled everybody up, would fill up our n equals 2 shell. So when we talk about the n equals 2 shell or level, what we are referring to is everybody that is pretty much encompassed on that energy level. And that means that if we were to put electrons, one goes into here, other one goes opposite way. And by the way, when you have options of multiple orbitals, they go in actually one at a time in the upwards directions, which is hundredal, and then they come back and pair off like so, just so you know. And if you add all that up, that is 2, 4, 6, and 8 electrons would max out this shell. So when we talk about this shell, we're talking about a level. We're talking about all the individual orbitals that are basically found in that level, basically the entire energy level, every single orbital, how many electrons you could put in there. Not to be confused with something like subshell or sublevel, it's sometimes referred to. So why don't you tell me or think about how many max electrons to fill a 3D subshell? So take a second, think about what you think it is. The first number here is 3, which means we're talking over here. And we're talking about the D subshell. The D subshell would encompass all 5 of those d orbitals together. And again, if you filled it up, it would go in this case, one at a time here. And then it would go back and put electrons in like so. And that means that we would fill it up with 10 electrons. So that is a subshell, or sub-level, it's sometimes referred to, as opposed to our first guy there where we're talking about everybody present. That is a shell or a level. So let's do one last one here. How many electrons in a 4f orbital? So take a second If you want, you can put it in the chat box what you think the answer is. How many electrons in a 4f orbital should it be? The orbital, remember that any orbital could actually only hold 2 electrons max. So the answer would be 2 electrons, because in this case, we're talking about a 4f orbital. Could be this orbital, which could only hold 2. Maybe this orbital, maybe that orbital we're talking about, maybe this one, maybe this one, maybe this one, or it may be this one. But regardless, we're not talking about everybody together, because if we were talking about all of them together, that would be a subshell. That would be the 4f subshell. But since we're just talking about an individual orbital here, this could only hold 2 electrons maximum. Any questions on that? So sometimes you may want to kind of figure out, how many total electrons there are in a shell or a level. And you could do that by, if you want to know how many max electrons in a shell or level, you could use this formula 2n squared. You actually square the number first and then multiply it by 2. So for example, n equals 1. That would be 2 times 1 squared, which is 2 electrons, which is what we see here. 2 electrons. We got to our n equals 2 level. That would be 2 times 2 squared. 2 squared is 4. 4 times 2 is 8 electrons, which are the 8 electrons that we just saw here. So in case you don't want to kind of draw this sort of diagram out, maybe you got to like the 4th energy level or something like that. Obviously it would be 2 times 4 squared. That's a lot of math there. So that's like 4 squared. They call that 16, I think. 16 times 2. Oh, I should get the calculator. We'll go 32 and hope for the best. And that's hopefully what we should have, obviously, through here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. It's a good deal. I'm not going to go any higher than that, but you could use that sort of formula there to kind of quickly calculate on a particular sort of level, the total amount of electrons. Any questions on sort of our quantum numbers here, how they relate? And again, these are sort of how, really, you learn electron configuration. They just kind of say, hey, it's 1s2, 2s2, 2p. But really, it's really based on these quantum numbers. This is how we figure out, for example, these theoretical sort of calculations. There's like 1 orbital here, or 3 orbitals here, and how many are on this energy level and how many are in that energy level. This is sort of the basis for how we get to our electron configuration, which we're going to talk about next, I think. Any questions on that? So there might be a question like, for example, we'll go back here. So we got up to L equals 3. Potentially, if we went to the 5th energy level, L would have values of 0 to 5 minus 1, which is 4. So that is 0, 1, 2, 3, and 4. So we already know this is S. That represents a P. That represents a D, and that represents an F orbital. So you may ask yourself, I've never heard past F, like what happens? And there is orbitals sort of past F, although we don't really come in contact with them all that much. And they came up with a very creative way after that. You pretty much go alphabetical after that. So G would come next, right? And you just kind of follow the alphabet after that, in terms of if you needed to identify what orbital you were talking about. If it was like L equals 4, it would be like FG, and H, I think, comes after that, and so forth. So you sort of follow the alphabet after that, until you kind of get to the end there of like 6, basically. Any questions on that? Yeah. All right, so Let's take a look here. So for n equals 3, determine the number of allowed subshells. We sort of, I think, did this guy already. And again, just to review, for n equals 3, that again is the energy level. And from that n equals 3 value, we would have a 0, a 1, or a 2. And again, the 0 would represent an S. And more specifically, because it's on the third energy level, it would represent a 3s orbital. 1 would represent a P, like we talked about, but also more specifically, because we're talking about n equals 3, it would represent the 3p subshell, right, which represents 3px, 3py orbital, and 3pz orbital. And 2 would obviously represent, as we talked about, D. And again, more specifically, it would represent the 3D subshell, which would represent, again, those 5 different D orbitals. Any questions on that there? And we kind of touched upon this guy as well as we were going through it. But again, just a reminder, obviously, L equals 2. Determine the possible numbers you could have. Again, M sub L goes from minus L to 0 to plus L. So you would start at minus 2, whole numbers like we did, plus 1 and plus 2, which again would represent our 5D orbitals in this particular case. Okay. All right, so we talked about these guys. Again, our s orbitals. Again, where they come from, as we just been talking about, is our quantum numbers. And again, this is our, in terms of M sub L, minus 1, 0, and plus 1 here. This would also be obviously for our D, minus 2, minus 1, 0, plus 1, and plus 2 in terms of our M sub L values. And obviously our 7 here for our F orbitals. So I talked about this a little bit earlier with the electron spin. But again, the reason was known as Pauli's exclusion rule, which again means, as we talked about, that really no 2 electrons can have the same spin. So the way that we get around that is 1 electron goes in up, 1 electron goes in down. And again, how electrons do go into the atom when there's more than 1 orbital is, as I mentioned there, and as we'll see, basically 1 at a time, and then they come back and pair up. So atoms with more than 1 electron, when we have electrons that are placed in particular quantum numbers, they do prefer a certain order in terms of how the electrons go into the atom. And when we have sort of, only 1 sort of electron present, everybody in terms of their orbitals with 1 electron present, like in hydrogen, everybody in terms of their orbitals are all equal in energy. So what I mean is, you go to the second energy level, the p orbitals and the s orbitals are identical in terms of energy. The third energy level, the s orbitals, the p orbitals, the d orbitals, they're all identical in energy. And again, electrons go in from the lowest until it's filled, go to the next spot, and again, continue in sort of this fashion until they fill it up and continue on. But what happens, though, as we get more than 1 sort of electron that is present, there's actually sort of a change in the energy of the orbitals. And what ends up happening is there is some differences in terms of where those orbitals sort of end up in terms of energy. So when we get to more than one electron that's present. Now, when we go to our n equals 1, we still have the 1s. When we go to our n equals 2, for example, we then have the 2s, but the 2p actually becomes a little bit higher in energy. And after that, then we actually have our 3s. We then have our 3p that occurs. And then oddly, we actually get like the 4s being next lowest in energy, followed by the 3D. So there's a shift in terms of the energy that occurs with these orbitals when we have more than one electron present. And that's going to determine how the electrons actually go in. So it's going to kind of follow what you would normally think. It would fill up that 1s, it would go to the 2s, it would then go and fill up our 2p. It would then fill up our 3s, obviously fill up our 3p. And then this is where some people run into problems. They assume, well, after 3p should go to 3d. But actually what happens is as these orbitals sort of move energy levels and kind of shift a little bit as there's more electrons involved. Again, these are all electrons which are negatively charged, not happy to be near each other. So they do try to spread out a little bit. And what ends up happening is that 4s orbital is actually lower in energy. So it would get the electrons first, followed then by our 3D. And that pattern of basically the s orbitals getting the electrons first, followed by the d orbitals, is a very common thing that happens with electron configuration. And again, when we have a lot of electrons involved, we get this sort of shift in sort of the energy levels and really their distances from the nucleus. And it causes sort of a different order in terms of how you would expect, most of the electrons to go in. And that's what basically these sort of graphs represent, sort of the distances as we sort of go from 3s to 3p to 3d and how far they could kind of get close to the nucleus and sort of penetrate far away in a wave type function. So what we end up with is the order of how electrons fill the atom. And the good news is you could kind of create it pretty easily for yourself. It basically starts, we know, with a 1s, and then you basically just run all the way down to 7, all s's. And if you remember, what we talked about was p orbitals don't start until the second energy level. So you start with a 2p and then run down to 7. And we talked about with our quantum numbers that Ds don't start to the third energy level. So you start to 3D, 4D, 5D, and 6D. And we talked about Fs don't start until the fourth energy level, 4F and 5F. So if you start up here and kind of go diagonal there, that's exactly what we were just talking about with our quantum numbers, where everybody kind of starts. And how we use this is we always start up here. That's where we start in terms of electron configuration. And we basically follow the arrows, kind of zigzag back and forth. Nice thing about this is something you can kind of recreate very quickly for yourself if you need to know the order of how the electrons basically go into the atom and so forth. So if you know this and you know what we talked about earlier, that if you fill up an s orbital on any level, that is 2 electrons. Fill up the p subshell, that is 6 electrons. If you fill up the d subshell, that is 10 electrons. And fill up the f subshell, that is 14 electrons. You pretty much should be able to write any type of electron configuration that you would need to. And we'll talk about writing that, I think, next time.